Okay, so now we're going to be working on, let's say, the harder part of this project, which is the Gillespie simulation. So just to give you a little bit of background on this, a lot of times we don't have the computing power, or there's just simply no analytical solution of our differential equations. So what we've done before in part 1 and 2 is find the exact solutions. Now what we're going to do in part 3 is do a simulation that is going to get us very close to the exact solutions, but not quite. So basically what we do in a Gillespie simulation is we have two reactions. The first reaction we're going to say is two zombies, or one zombie and one human meet. What are the two possible outcomes? What are the two reactions that can occur? The first outcome, or the first reaction, is that the zombie wins the battle against the human, and the human becomes a zombie. So basically a person, zombie meet, then the outcome is a zombie and a zombie. So you lose one person in S and you gain one zombie in Z. What is the second possible outcome? You have a zombie and a human meet, then the human kills the zombie. So you lose a zombie, but no change is done in the S, because you have R is like the cemetery. All the dead zombies just go to the cemeteries. They don't go back to being humans. So now what we're basically going to do is we're going to calculate kind of like a probability of either of these happening. So what they depend on is how many zombies and how many humans you have. That's one of the probability factors, and also this alpha factor. So the first thing that we have to do is to understand that we're going to be calculating A1 and A2 and then comparing it to a random number. If A1 over A0, A0 being the sum of A1 and A2, so you have it here, A0 is A1 plus A2. So if A1 divided by A0 is bigger than a random number, we're going to let Matlab come up with a random number, then reaction 1 happens, which means this 1 happens. And then you gain a zombie and you lose a human. You gain a zombie and you lose a human. Now, if A1 over A0 is actually smaller than the random number, the human wins and you lose a zombie, and your human population remains the same. Now the next thing that you have to know is that these interactions have a particular time they take to happen. So for example, you can have your human and your zombie fight for an hour, and then at the end the zombie wins, or it can happen very quick. It shoots him in the head and it's done. So this is what this tau is determining. The tau is determining how long your interaction lasts. And we need to calculate a tau, because what we're going to do is we're going to start the simulation at time 0, and we're going to let the simulation run over time until either all the humans are gone or all the zombies are gone. So until either one of our groups becomes 0, we run the simulation. So the first thing that we need is our alpha, which is 0.6. And the next thing we do, so for part 3 initially, if we go for part 3, the first thing that you want to do is you want to basically redo part 2, just the first part of part 2. So you're going to solve the differential equation for S0 when alpha is 0.6 and your initial zombie concentration is 4. So you just have to redo that little bit of part 3. That's just going to give you the exact solution to this problem. So your first thing is your alpha, then you're going to have, you have to put your function again. So it's basically the same thing as part 2 here. You're going to do your function, then you're going to solve your differential equation, and then you can go ahead and plot it. The only thing that you have to be careful in here is that your zombie population initially is 4. So then you have to calculate what S naught will be. Same thing as you did for part 2. Now, after you plot it, you can go ahead and hold on. Or we can hold on later. Yeah, you can just go ahead and hold on. So we're going to plot this, and then all of our simulations are going to be plotted in the same plot. Now, the next thing that we have, as I told you, is, okay, so we need again our n, which is 400. And we also want our seed. So when he talks about seeding, let me explain to you what that is before I go into the simulation itself. So he goes on and on talking about what a seed is and random numbers is, and I'm going to tell you what that means. So when you make a random number, the function to make a random number in Matlab is called rand. If you say rand 1, you generate a random number from 0 to 1 following a Gaussian probability, right? If we do rand 1 again, we get another random number. You do rand 1 again, we get another random number. So right now we have 3 random numbers. And every time we do rand 1, we're going to get a different random number. Don't get confused and do rand 1 and then rand 2. What the number inside means doesn't mean the number of randoms you have, but it means the size of the random number. So if you do rand 1, you get a matrix of 1 by 1. If you do rand 2, you get a matrix of 2 by 2. So always do rand 1. Now, if we look at here, we have a random number 1 of 0.8, 0.9, and 0.1. If we keep on doing rand, we're never going to be able to replicate this sequence of random numbers. If we want to be able to always get the same random numbers, we have to seed the randomness. Basically, we're telling Matlab to begin from the same place every time. So for example, if I now do seed equals 1000, and now I tell Matlab to seed my randomness, which I do by doing RNG, and I do seed. And now I do rand 1, and then rand 1, and then rand 1. I get 0.6, 0.1, and 0.9, right? Now if I seed again, and now I do rand 1, we see that the first random number is the exact same as the previous one. So if you understand what I just did, basically what we're telling it is start from the same point you did before. And now if I do rand 1 again, we get 0.11, which is the same one we did before. Doing seeding is the only way you have to ensure that your sequence of random numbers are going to be the same every time. Now, we want to have this at the beginning of our simulation, because if we have a crazy number of random numbers showing up every time we run the code, we're going to get a different graph. And we want to get the same graph every time. So the first thing that we're going to do is we're going to set up a seed. We can do it of 1000 to begin with. And then we're going to say, this is just a part of code that you kind of need to know, but it is an RNG, which is going to tell Matlab that your randomness is seeded. And we're just going to say seed. That's all we need to do. But you just have to understand that this allows us to have the same sequence of random numbers every time. So now what we want to do next is begin our time. So we want our time to start at 0. Then the next thing that we want to do is we want to tell them how many zombies we have initially. So you tell what C is, and you give it the initial number. What in this case I think is 4. Then you tell it what your S population is. So basically, if we're gonna follow the algorithm, the first thing you need to know is what Z is initially and then what S is initially, right? Now, after we have these two values, we can go ahead and calculate A1 and A2. We already know what alpha is, right? Which is here, which is right here. So then what we do is we calculate A1, then we calculate A2, then we calculate the sum, because we need the sum for the random part, right? So, and then for the time part too. So then we can calculate, we can call it A0, same as in the PDF, and A0 is just going to be the sum of A1 and A2. Sorry, I know this looks messy, but it doesn't matter. Okay, so now we have A1, A2, and A0, which is all the numbers we need, A1, A2, and A0. You can go ahead then and calculate what your tau is. So to calculate tau, just follow this equation. So minus 1 over A0, natural log of R1, and R1 is just your random number. So just, you don't have to call it, you can either do R1 equals rand 1, So for this simulation, you're going to need two random numbers. The first one is used for the time the zombie-human interaction, and then the second one is to decide whether the zombie died or whether the zombie turned the person into a zombie. So you need two random numbers. This is the first one, so you can call it R1, or you can just say R1, rand 1. So we just type this equation, minus 1 over a naught, natural log of rand 1, and that's your time step. And then the next thing we need to do is we need to create a condition. So what is the condition? Is A1. Now we make the A0 divide on the other side, and we say A1 over A0 has to be bigger than R2. If A1 over A0 is bigger, then we say reaction 1 takes place at time t plus tau, which means this happens. So let's create that condition, which is going to be A1 over A0. That is the number that is going to tell us what's going to happen. So just do A1 over A0. That's your condition. And now, if we want something to happen if a condition is met, we can use the if statement as we've done in the past. So in this case, we can just say if our condition is, in this case, bigger than our random number, so we can just say condition bigger than random. Every time you do rand 1, it's going to be a different random number. This doesn't mean that we're using the same random number as before. It's a different random number. So if this condition happens, now we have to change our S and Z variable. So if condition is true, if the condition is bigger than our random number here, then what happens to S and Z? So that's what you have to update. You have to give S a number and then Z a number. So if condition 1 happens, we lose a human, we lose it, right? So you subtract 1, and we gain a zombie, so you add 1. Now, what happens if condition is smaller than random number? Then you can use else. So if it's not bigger than it is, smaller or equal, so you don't have to put else if, you can just say else. Then else, what happens? What happens if this number is actually smaller? Then reaction 2 happens. So again, you have to update what your populations are. So if a reaction number 2 happens, the S remains the same, but then the zombies lose 1. And then you end your condition. If we leave it how it is right now, we're only gonna get it to go one time, right? But we want this to keep on happening, and we want this to keep on happening until either all the zombies are dead or all the people are dead. In order to do that, we can use a while loop. The other thing that we want to do is we want to plot, every time this happens, we want to plot it. So every time the Gillespie algorithm happens, we're going to have a value of total zombies and a value of total humans and a time. So we want to basically see how the zombie and human population change as a function of time. So to do that, what we have to do is just add a while loop right after our first S. So this one is just our initial conditions, right? And these are going to be updated every time. And we can add just a while loop. Remember that, so for a while loop, you need a condition. Remember that the conditions in this case are either S or Z are 0. So basically, we can say if while S is bigger than 0, right? And then if you want to add a second condition, you just have to add the and sign twice and then write your second condition, which is S bigger than 0 and Z bigger than 0. You want this to run as long as both populations still have someone. Then when either of them becomes 0, the simulation stops. That's what a while loop does, right? The only thing else that you guys need to know is that before the while loop, just make sure you have you plot the first conditions. So here, just start by plotting the first condition. So just do plot t comma s, and then I would advise you to plot this as points, and it's because every run is going to give you 1 point. So it's very important that you select the color you want. I'm going to make it blue, and then just put a point. This means that a period. This means that t is only one number and s is only one number, and put it as a dot. And then do the same thing for c. So now plot c. Same thing, you can make it a different color. You can make it red if you want it to match your first part of your graph. So now you plot the two of them, and then you just repeat this plotting right before the end of your loop. So right before the loop ends, right before it restarts, you plot it. So every run you plot 1 point. The other thing we're missing here is we created a tau, but now we need to update the time. So every time an interaction happens, it takes a certain amount of time, which is determined by a random number. But now we have to update the time. So to update the time, you just do t, which was your old t. It began being 0 here, but now it's just whatever your old t was plus tau. And that's going to be your new time. I think that's all you have to do. Just make sure that your A's and your taus and your conditions, all of these is well typed and you don't have any spelling errors. That's where I've seen most of the problems with this part. Now, the second thing you have to do is he tells you to seed it to different numbers. Basically, what that's going to do is it's going to have, if you run this only once, you're only going to get one plot. So one plot. But we want to run it more than one time to see if it converges to the same number. You normally want to do this with stochastic simulations because every time you run it, since it's random numbers, you can get a different solution. So we want to run it more than once so that we get more than one solution. In order to do that, you just have to set it to a different number. So you can again make a for loop, or you can just copy and paste all of this stuff and then just make seed a different number. So I would advise you to do a seed of 1,000, then 1,500, and then 2,000. 3 lines is enough. Seed it 3 different times and then run this. Remember to do the RNG again and then run the whole thing. So you can either put this seed in a for loop and then just run this whole thing 3 times, right? Or you can just copy and paste and then you change the seed every time. And that's going to give you three different graphs. I'm going to show you how mine looks like in a minute, and then you can compare to see if it's similar to yours. I hope this helps.